Hello everyone, and welcome to my presentation designing condensate drainage from reboilers. But first, a small disclaimer, please. I'm only providing tips and concepts today, not specific recommendations. So if you want to discuss any application, please contact me after the presentation. Thank you. We're going to start with a kettle reboiler that's got steam inlet control and an outlet steam trap, and there is the trap. The trap has to be selected and sized properly, but there are three other items to consider: why we would have a drop down to the trap, why a float trap is preferred, and why a check valve should be on the outlet. So I'll start first with why a drop down to the trap. If there's a long horizontal run before a trap, the condensate volume is so small relative to the mass that it can not only partially fill the pipeline, not completely fill it. And vapor could run across the top, collect in the body of the trap, and as more condensate tries to come in, it gets compressed, which impedes the flow and could cause a backup into the reboiler. So we don't want to see that happen because it would affect the duty. So the simple solution, which you see on the bottom right where the ellipse is just to install a drop down to the trap. And then of course, after the vertical drop down, don't install the trap too far away. So that's the first one that we want to consider. And the next thing we want to consider is the float trap. Why a float trap? So you see inside of the window that there's a steam above the condensate level. The condensate level stays above the orifice, but even as the flow changes, the beauty of this is you still always see steam. So as the control valve is adjusting to the demand, what happens is you don't get backup into the reboiler, and that allows you to maintain, the duty that you want over the full tube set. Watch the float trap in operation. There you go. The next thing I want to discuss is flashing condensate and how that has an impact, especially how it has an impact on the back side of a steam trap on the outlet side, which is why we need a check valve. We're going to take a look at vertical condensate returns and collapse hammer. So if you recall from the prior presentation, this is a video shot of acrylic piping solidly filled with condensate. It's in TLV's R&D lab in Japan, and the pressure is around 7 or 8 psi. When you take hot condensate through a steam trap, it's going to have flash steam because it's coming from a high pressure to a low pressure, and that flash steam creates a pocket, and those pockets can collapse. Watch how quickly those pockets can dissipate and collapse, creating collapse hammer where the shock wave is directed to the pipe wall. Here we go. I think that's just an incredible video to see how quickly steam pockets can collapse. Now let's take a look as we're feeding a horizontal line into a vertical riser, and you see the pocket on the left in kind of a pinkish color. There's a lot of vertical head when we're going 30 feet or so overhead into the return header. We may have header pressure of 25 psi or more. That is going to create pressure on that pocket of steam, and it's going to compress it, such as you see on the right. Now, if that pocket collapses, it'll create backslam impact during the collapse, and that's going to go back towards the trap. So we install a check valve after the trap so that the trap is not affected by the backslam hammer. So as a designer, you'd like to know, can I use a steam trap? Well, yes, you can if you have gravity drainage or a positive pressure differential at all times, and that's the lowest cost option. But then the question comes, well, when do I need to install a power trap? I'm not really sure. So I know that a power trap will evacuate the drainage body with a secondary pressure, but when do I need those versus a steam trap? Well, let's take a look at this application which has a steam trap on it. And let's imagine that that steam trap did not have enough pressure differential across it to lift condensate into the return header, so it was being dumped to grade or the system was on bypass. The solution for that is just maybe to lift it 2 or 3 feet up into an open receiver, put a pump only, and then deal with the flash off of the open receiver, such as maybe put a vent condenser there. But now, instead of being an open bypass or having a trap discharge into grade, you can pump the condensate overhead. Another way to handle such a stall condition, and we analyzed the stall chart, the extended stall chart, and how to mitigate it in the previous session. This is the extended stall chart that I developed and we analyzed in the previous session. But in the previous session, if you look here, P2 was 115 and P3 was 115 to keep it simple. But I'm going to change this P3 pressure now to 108 psi, which is going to reflect the pressure drop through the reboiler. Watch what happens. Here we're looking at estimated process condensate loads with a range of 70% to 100%. And we're dealing with 55% of oversurfacing. Now take a look at the steam pressures. Because we have so much surface area, at full load, the pressure drops down to 19 to balance with the demanded heat. And at 70% of load, it drops down to -1. We're in vacuum. But as the equipment becomes fouled, the UA value drops down to the point where it's similar to having an area of over only 100% of surface area. That's the bottom chart. Now look at this. The steam pressure has to adjust for that loss of area, and it jumps up to 108 at 100% of load. Isn't that amazing? So our range of load and our variance is from 70% at clean tube surface to have a -1 to 100% of load at 100% of surface area to have a pressure of 108. That's 109 psi variance. How would you design for that? That's why it's important to study the P3 minus P4 value to understand what your pressure differential is going to be throughout the expected operation of your reboiler. And it can easily be discussed the proper drainage method to use, whether it's trap or pump trap. If you do have to use a pump trap, here's a secondary pressure drainer, power trap design. There's someone that's just around 6 feet tall, and we like to get that 60 inches height at the bottom of the reservoir because that allows us to use the least amount of pump traps by having that 60 inches of height. So let's look at some design parameters for a pump trap. We're going to look at the motive in, the exhaust out, and the reservoir vapor space. There's our kettle reboiler, and there is our pump trap package. Let's study that a little more closely. The first thing is take a look at that blue line right there where the ellipse is. We'd like to see that outlet flange about 80 inches high. That's really important. We can work as low as 40 inches high, but having it 80 inches high gives us the least amount of pump traps required. The next one is if we take a look at the gravity drain coming into the reservoir, we can work with that second blue line at 60 inches. That's our preferred. We can work as low as 30 inches, but if you have an 80-inch height on the outlet flange, then we can get a 60-inch height here at that blue line, and that allows us to use the least amount of secondary pressure drainers. Now, the next thing I want to pay attention to is this balance line in red. That has to have no loops in it, and it has to connect on a tube side steam set exactly to where it's shown here. We're going to cover that for proper breathing in this next session about the motive valve, which provides the secondary pressure to push the condensate out, the exhaust, which have to vent the vapors out of the body so that condensate can fill the body, and why it's important to have no condensate pooling in either one of those motive or exhaust lines. So here's a power trap, pump trap, condensate in and out, motive in, exhaust out. So in order for condensate to go in, there will be vapors in the body. They have to be exhausted out freely. Let's pay attention to the breathing. The proper breathing of a pump trap is very similar to a snorkeler. A snorkeler has to be able to breathe, get air in and exhale it out, in and out. And it's the same thing with a pump trap with no obstruction. So here we've got a motive supply. This is our steam supply to the power trap. Motive in, motive supply goes into the power trap. I want to pay attention to this yellow arrow. That dimension is really critical. Condensate, we don't really want condensate to go up past the trap set on the left. If the condensate goes up into the motive supply, that'll bring debris into the motive valve, and it'll also choke the motive valve, and it will adversely affect performance. So the selection of the motive trap and the check valve after it is quite critical. For example, we never recommend a bucket trap. We never recommend a disc trap or a thermostatic trap, even if it's TLV products. We recommend a free float or a float trap so that you can get a quick discharge, and that keeps the condensate from going into the motive supply, and it gives you nice inlet breathing with the steam supply. The next thing to look at is the exhaust. In order to get condensate to fill the body, we've got to be able to exhaust the vapors out. But steam can come down that pipeline and build up a water head. We don't want that to be too high because that'll be a restriction, kind of like putting a rag in the exhaust of a car. So we don't really want to see that condensate build up. And let's talk about the design of exhaust lines. So there's the car. We wouldn't put a rag in the exhaust because that would stop it from discharging. And the same way, let's take a look at our snorkeler. If our snorkeler would have to breathe out through a loop, well, that loop could collect water. That would be really hard for that snorkeler to exhale the air. We want him to be able to exhale the air quickly. So no loops, please. And it's not only the same for the snorkeler, but it's the same for a power trap. No loops, please. Ideally, we want the exhaust to lift up less than 10 feet. That's usually really easy to accomplish into a reservoir. We don't want to see it above 10 feet because that's too high. The condensate level can build up too high. So that's really not good. So it has to be less than 10 feet. It's easily done. But if there is some unusual circumstance that it has to go higher, we can still do it, but we just have to install the special piping such as you see on the right-hand side. Let's talk about balance points. This is critical. If you've ever used pump traps before and you've had a problem, I'm going to bet that you had a bad balance point. So we're going to talk about level pot balancing, channel head tapping balancing, tapping at the control valve inlet side or at the control valve outlet side, and why it's important to have no loops. We're going to start with the level pot. Level pots typically are used before outlet control valves. So we want to get the condensate to go through the control valve. It's got to be able to enter the level pot. So there'll be vapors in the level pot, and those vapors have to be pushed out so that you can let the condensate come in. So the balance line is critical that you can get the vapors to go out. Otherwise, the vapors will compress and there'll be a resistance. So the easiest way to get the balance line to work and allow the the condensate to flow into the level pot is to have the same pressure as a condensing source. Condensate is coming from the condensing source. And if you have the same pressure at the top of it, it's easy to push that back up and get flow to occur by gravity. So here, let's say that your condensing source is 115, and you bring 115 there, now you have gravity flow going into the level pot. It's quite easy to get discharge. But now let's take a look at this level pot on the right. And let's say that we had 115 from the condensing source, but it wasn't balanced properly, and it was balanced to 150 psi. So that brings 150 psi into the level pot. So how do you get condensate to flow from 115 condensing source when you have this line connected? And if you restrict that balancing, then you're defeating the purpose of having a balance by compressing the vapor in the top of that level pot. That's really a problem. So we wouldn't want to do that. That's a big restriction to gravity flow. So we also see some problems with a balance restriction if that pipeline there, if that valve is a restricted bore, it should be a full bore. Now, it is possible that it might be connected somewhere such as to the inlet side of the reboiler after the control valve, and that pressure might be greater than 115. You can get flow into level pot if you have enough height to get the filling head to overcome that distance. But if you don't have enough height, that won't work. It's usually just safest to properly balance it over to the condensing source if you can, so you don't have restrictions of flow, and then you can get gravity flow. All right, so let's take a look at balancing, and here what you're seeing is I show a level pot or a reservoir. So a level pot's used with a control valve, a reservoir is used with a pump trap. There are some subtle differences, but first of all, let's take a look at balancing to the inlet side of a control valve. This is really not a good idea, and I'm going to explain why. So let's take a look at the pressure on the inlet side. It's P sub X. We're going to bring that pressure balance down to the reservoir level pot, P sub X. We're going to take a pressure drop through the control valve to P sub Y on the inlet side of the reboiler. We also call this P2 if you attended the first presentation. This is the P3 or PZ, if you will, after a pressure drop through the reboiler. So now let's put some values to it. There's 150 pound steam going into the valve, and we just brought 150 pound pressure into the level pot or reservoir. There's 120 on the outlet side of the control valve at full load. And then the pressure drop, let's say, is 115. Now, here's the problem. First of all, you can see that 115 is not going to flow into 150, but that's the best condition, because the worst condition is when that control valve throttles down and the delivery pressure where 115 is, it now becomes 20 psi. How can you get 20 psi to flow into 150? And what we'll see happen there is people will put valves on top of the level pots and they'll be bleeding off steam because they don't really realize, well, they have a pressure imbalance. So the 150-pound steam is going into the level pot, it's being bled off with a valve. It's not good to balance on the inside of a control valve for that reason. It's a very strong negative pressure differential. So let's look at the next situation, which is balancing, if you will, to the outlet side of a control valve just before the reboiler. So there's our piece of Y pressure, and we're going to bring that down to the level pot. Here we go. There's piece of Y at the reservoir, the level pot, and piece of Z there. Let's put some values to it. So now our pressure balance is 120 into 120 into the level pot. So our outlet pressure of the reboiler is 115 into 120. If that level pot or reservoir is really close to the reboiler, it's not a sufficient fill head to get flow. Now here's a difference between a level pot and a pump trap, a level pot and a reservoir. If you have a lot of filling height, so let's say the reboiler is 20, 30 feet overhead and the level pot is at grade, you can fill that level pot because you'll make up for the difference of the pressure. But you cannot do it with a reservoir because in addition to having the necessity to flow condensate into the power trap also has to be able to exhaust the vent steam back into a condensing source. And it cannot vent it into the condensing source if the condensing source is 120 psi. It's a restriction to the power trap and it negatively affects performance. So it's a negative pressure differential. It's a weaker negative pressure differential than we had originally with the inlet side balance, but it still is not a desirable idea. The best place to balance is going to see right here on tube side steam, and that is balancing to the condensing port, the condensing part of the reboiler. So here we have a channel head tap. That piece of Z pressure is going to go over to the level pot or the reboiler. Now they're exactly the same pressures. The level pot and the pump trap have just become the lower extremities of the reboiler. You get beautiful gravity flow. It's the same pressure, and that gives you the least restriction, only pipe restriction, which basically goes away to nothing. And that's how you get adequate drainage into the level pot or reservoir. It's the best way to do it, by a channel head tapping gravity drainage with positive pressure differential. So let's take a look and put that into play. We're going to focus on this package right here, pump trap package. We want the condensate to be able to freely flow in. In order to do that, we've got to be able to vent out the vapors in order for it to flow in like that, and that's done through the proper balancing. That's why it's important to maintain a vapor space in the reservoir so that you can balance from the power trap into the reservoir and then from the reservoir back to the channel head tapping. And that condenses the exhaust steam. We also have to have an air vent check valve combination there because incondensables will form and they have to be pushed out through that air vent when it's in positive pressure operation. And yet it sometimes at low load will go the negative pressure operation. So we don't want to get air infiltration. So the check valve prevents infiltration. We use full port valves, not reduced port valves in the balancing. And it has to connect at the proper location and with the proper size, which I'm going to review later on. Here we go. So if you look at the bottom chart, if you have a 1-inch tap at that proper location, you can work with one pump. Sometimes we see something like a 3/4 inch tapping. That's really not big enough. That's a restriction. But if you've got to use 2, 3, 4, or 5 secondary pressure drainers, do you see that that tapping needs to be 2.5 inch, or in your case, maybe 3 inch, because you like to use 3 inch instead of 2.5 inch. So each power trap gives around 13,000 pounds an hour. If you're dealing with around 35, 36,000 pounds an hour, you need 3 power traps as a minimum. That means you need a 2-inch connection. If you're going to put an installed spare, you need a 3-inch connection if you want at least 2 or 3 inch. If you're not sure when you order new equipment, why not just order it with a 3-inch tapping? It's very small added cost relative to the price of the reboiler. And the alternative is if you find out when it's in the field that you need a bigger tapping, that's so expensive to tap it and recertify it in the field. So with new equipment, why not just order it with a 3-inch tapping so you've got it covered? I will say this, when you put a package in on a reboiler, an existing reboiler, it's a certain investment. And if you don't have the proper location and the proper size, they're not going to balance properly. They're not going to work right. You cannot make 4 pumps or 3 pumps work well with a 1-inch tapping. And I think that that would be an improper operation, and you would be dissatisfied with the performance. So please pay attention to that bottom chart. Proper balance size is essential. Proper connection size is essential. And we need to keep the vapor space in the reservoir. Now, we have our pump trap body filled with condensate, and we're going to bring some steam in, and it's going to push that level down. That's how we pump it out. But we need to make sure that that steam line is large enough. So let's take a look at the chart at the bottom here, and you see if you've got more than one unit, 2, 3, 4, 5 pumps, we need piping as large as 2.5 inch, or again, 3 inch. So it's kind of funny. I mean, sometimes we walk on site, there was one of the applications we looked at not that long ago, had 3 large pumps on it, and it was being fed from a manifold that was a 1-inch manifold. Well, how can you feed 3 pumps without starving the steam going into the secondary pressure drainer when you need a 2-inch line and it had a 1-inch line? Okay, so when there is steam in the body of the pump and it's pressurizing the pump to push the condensate out, new condensate coming in, such as what I've just shown here, it can't enter because there's pressure inside the body. And that's why the X is flashing. So it has to be able to back up into the reservoir, and that's why we need an adequate reservoir. And still, that reservoir needs to maintain the vapor space so that we can properly balance. That's why a reservoir has to be properly sized. And then we can balance into the reservoir and back up into the channel head so we have a nice balance, and then we can condense the exhaust vapors. That makes for nice power trap operation. And then when we go through a new cycle again and we've balanced it properly, we can get more condensate in there. So do not restrict the motive size. Do not restrict the balance. Sounds familiar, right? Do not lose the vapor space. I know we might have heard that before. Okay, let's take a look at equalization to a shell side steam reboiler or heat exchanger. It's really rather simple to balance to a shell as long as there is the right tapping size and a vapor space. We just have to make sure there's no loops. There's the proper size tapping. So no piping loops. We're going to connect to a vapor space of shell side steam, and there needs to be a large tap in the shell. When you're ordering new equipment, if you're not sure, why not just order with a 3-inch tap? You can always reduce that tapping down to 1-inch, but if it's a 1-inch tapping, it's so hard to get it up to a 3-inch tapping. Tube side steam equalization is much more critical and challenging. I know that people just are trying so hard to connect that balance line to the outlet line, but look at that. That line is just too small. You cannot get counterflow through that line. It is not going to work. And you can't connect it to the inlet side. The only place to put the balance line is right there in the channel head below the divider plate. So no piping loops, below the divider head plate tapping, a large tap in the head. Again, if you're not sure, just order new equipment with a 3-inch tapping. You can always reduce it as needed. I thought I would show you some specialized designs. Sometimes you have a tight installation with existing equipment, so we can do a layout design like this to put 2 power traps in there and all the motive and manifolds, and the balance is appropriately done, and you can see the balancing and everything right there. And that way we can design it to fit between existing equipment. Here's another interesting one. We like to see this outlet flange, ideally 80 inches high, but this was a really low one. So what we had to do is put a loop down here and design into the reservoir. We had to extend the reservoir, and we had to come into the center of the reservoir. So it was longer, and we came into the center rather than near the top in order to fill into the pump traps. We're paying attention to that water level line to keep it below the tube bundle and the reboiler. We don't really want to flood those tube bundles. We need to maintain a proper balance going into the channel head with the proper size tapping. It was able to be done with an ultra low fill head. However, the cost to do that, besides using like non-standard tank, is also that it probably needs an extra SPD in order to do that because of such low filling head. That's why on new equipment, if you can go 80 inches to that flange, it's the best. In the first presentation, I showed part of this case study, but I thought I would show you this vertical thermosiphon reboiler and why they were wasting condensate with the whole application. So we start off with the condensate header, having hot flashing condensate at 1.8 bar. We did have 3.7 bar, so the original designer might have thought that was enough, but the reboiler was so oversurfaced that the pressure was 0.35 bar on the original design. So that's a negative pressure differential. And what do you think happened? So what happened was they dumped the condensate to grade for over 10 years. Well, somewhere in that time period, they said, well, let's just change the transmitter and let's flood more of the reboiler. So we just use very little of the surface area, the duty. And there you can see the pressures jumped up to 2.2 bar, which was great. But as you saw in the first presentation, if you watched it, it dropped the temperature down to 94 C because of the high residence time. And the exit temperature was 92 C, taking this colder condensate into flashing condensate header at the top, created collapse hammer. So again, they had to discharge the condensate to grade. So here's a recommendation for them to go back with the steam using the full surface, which gives you, a really easy dynamic to fix by just varying one variable, the pressure. And we put a pump trap with a reservoir. So you could not originally get the condensate to flow out from 0.35 bar to 1.8 bar, but that's why you bring the secondary pressure in here of 3.7 bar. And now you've got a nice differential from 3.7 bar to 1.8 bar. You have a 1.9 bar differential, and you can return that condensate into that header. And if you're worried about flashing, one of the things you could do is consider the concept of side entry or bottom entry. So for those of you that didn't attend the first presentation, this is a bottom entry concept. If you didn't want to discharge condensate, if it was colder, for example, into the top where the flash steam would be and it might create collapse hammer, why not just put a long pipe down from the header? And this is a concept. Put the discharge condensate into that bottom of the pipe and let it flow up into the liquid level in the header, which is larger. It would be critical that this has no chance of steam entry, so it has to come from a pumped application. It cannot come from a control valve. If there's any steam that gets in there, it could create quite severe collapse hammer. So pumped condensate only, cannot use with an outlet control valve because steam can blow through. Understand that a power trap discharge is 8 gallons per cycle normally, but there's a throttling valve there. You could reduce the amount of flow at any particular interval and extend that interval so it more smoothly integrates. This is a concept that requires no chance of steam. And since it's a concept, it would have to be reviewed by a knowledgeable engineer looking at the application, has-opping the application, and make sure that it's safe to install this type of an installation. I thought I would show you an interesting case study, which is kind of one of the funny things that we see sometimes on the site. So here is a reboiler production problem where they were having problem with reboiler A being ineffective. But first I'm going to show you reboiler B, which was effective. The pressure was 125 going to a tank around 14 PSI. So that was good operation. But they had a problem for some reason and it was off design. They were using steam from the 14 PSIG tank, if you will, the line off of the tank, going through the reboiler. And they were putting that condensate and trying to lift it back up into the tank, and that reboiler was flooding. So what must have happened is the reboiler A originally must have had 125 pound steam pressure, and they decided to use like vent steam or low pressure steam for it. and they thought that would be efficient, and it would be efficient. It's great to do that as part of the steam balance, but we have to look at the overall operation. So in this case, the outlet of the reboiler was so low that we couldn't get a pump trap in there, but you could make a recommendation to come out of it with a steam trap and discharge that into the pump only, bring in the secondary pressure here to pump it out, and that gives them the best of both worlds. They put a pump in there, they get to use the low pressure vent steam, so that improves their steam balance and they're not venting so much, and they get the operation of reboiler A. Everything is working well then. So for system design, that type of specific equipment procedure is necessary. We like the sites to provide us with the full system data, and then we do a stall analysis through our program software. It's automatically uploaded. An extended stall chart is made for every single process application. It'll look something like that if we look at the record. We keep all the data points. There'll be about 8 to 10 pages after each record of data that's generated. And then from that, and the discussion with the client about the demand load range, we'll select a basic drainage system, whether it's a steam trap or a pump trap. And we maintain those records digitally. Now, before we provide those records back, every single application must be reviewed by 4 individual members at TLV. We can also provide details so that people can see the flow into the reboiler and get a basic idea what the piping is accomplishing in terms of fluid dynamics. So that is provided also at no charges if it's ever needed. I hope you enjoyed this presentation, Designing Condensate Drainage from Reboilers. I'm available to answer questions now, please, and at any time, please feel free to copy this sheet and contact me for any applications that you have. Thank you very much for attending this presentation.